Hello and welcome back to the FluidXAV channel. This is part 3 of our modeling transient compressible flow series. So far, we have created the nozzle geometry in SpaceClaim and generated a high-quality poly-hexcore mesh using Fluent Meshing, as you can see in this picture. In this video, we will move into the ANSYS Fluent to set up the physics, run the simulation, and analyze the results. We will start by importing the mesh and configuring the density-based implicit solver for compressible flow. Then we will define material boundary conditions and operating pressure. After that, we will compute a steady state solution to initialize the flow, enable time dependent, and apply the wave-based outlet pressure. After that, we will compute a steady state solution to initialize the flow, enable time dependence, and apply the wave-based outlet pressure. To improve the accuracy around the shocks, we will also enable automatic mesh refinement, allowing Fluent to refine the mesh dramatically based on the pressure and the density gradients during both the steady and transient stages. Finally, we will run the transient simulation and review the results, including pressure contours, Mach numbers, Mach number distribution, and mass flow rate history. So if you are ready, let's open Fluent and begin with the setup. So let's get started. Okay, so I will run the Fluent launcher, then select the solution under the Fluent launcher, use double precision and 4 processors. I will work on the same directly as the previous tutorials and then press on the start. Okay, now we are in the ANSYS Fluent mode. First of all, I need to read the mesh we generated before in the previous session. I will select the nozzle mesh and press on OK. And, press the display mesh, select all and display the geometry. I can use the isometric view and then also deactivate this boundary markers, hide it. So here I can go here, select the edges and use outline, and you can also change the color and then display again. So this is our geometry. You can also select the edge type to all to see the meshes. So I will select this one and and use the display and then close. You can see the mesh, the boundary layers around the walls in both sides. And also here, as you can see, this is our mesh. It's a coarse mesh actually, but we will use the mesh refinement for our problem. After that, I can go and do the perform mesh. So you can check the minimum volume. So there's no error here because it's a positive value. It's okay, and you can use the evaluate mesh quality and check the quality of your mesh. And as you see in the previous sessions, the first session, the boundary conditions are pressure and the units are in atmosphere. So to change the units, you will go under the domain mesh and select unit. Then click on one of these quantities, and then on the keyboard press P, and then find the pressure. Here it's a pressure, so click on the pressure, choose the atmosphere by clicking on it, and then close this window. So this is actually a density based problem. You can select and change the solver type to density based. I will change this one to density based by clicking here. And from this time list, I will keep this steady for now. We will start with the steady flow and then finally change the transient. So for now, I will keep this one to the steady. So it means that we will solve the steady flow through the nozzle initially. In the later steps, I will use this initial results as a starting point for a transient calculation. So at that time, I will change this one to transient. Then I can go to the physics here, and under the model, I will activate the energy equation by clicking on the energy equation. Next step is again under the physics and models. I will use the viscous model. You have access to different options for this model. In this case, I will keep the default value, the default K omega with the SSD turbulence model, K omega model. So I will press on OK. So now I will go to the outline view, and then I will go to the material, and under the fluid. So I will right click and edit the air as the default material for the fluid here in the ANSYS Fluent. So the only change is here I will change the density from constant to ideal gas for the air, and retain the default values for all other properties here in this list, and press on change and create, and finally close this window. Close this create edit material by clicking on the close. Then after that I will go to the physics solver and operating condition. Click on it, open this operating conditions here, and then change this operating pressure from 1 atmosphere to 0 atmosphere. So since you have set the operating pressure to 0, you will specify the boundary condition inputs for pressure in terms of absolute pressure when you define them in the next step. So boundary condition inputs for pressure should always be relative to the value used for the operating pressure. So I can just press on OK and close this operating condition window, and then go for the boundary conditions. First of all, I will go to the boundary, but before that we can check our cell zone condition, which is a fluid. The name is solid 1, but it's a fluid type, as you can see here. You can see it's a fluid type. You don't need to do anything because you have just one material, and it is in the it's a default value, and the material is air, so you can keep this one as it is. Just directly go to the boundary condition, and for the inlet we have inlet, pressure inlet. So I will double click on the pressure inlet to open the pressure inlet window. If we go to this problem description, you see the inlet pressure is 0.9 atmosphere. So we can define this pressure here. So for the gauge total pressure, I will change it to 0.9. And also for this supersonic or initial gauge pressure, as you can see, I will select this 0.7369. So this is 0.7369. The inlet static pressure estimate actually here is the mean pressure at the nozzle exit. This value will be used during the solution initialization phase to provide a guess for the nozzle velocity actually. And finally, I will retain the intensity and the viscosity ratio here, and I will change this turbulent intensity to 1.5 and keep 10 for this viscosity ratio here, and then finally I will press on apply and close this window. Now I will define the boundary condition for nozzle exit. So I will go to the outlet, and as you can see, it's a pressure outlet. You can double click to open this window to edit different parts. So for the gauge pressure, enter 0.7369 atmosphere, and the same as inlet, I will keep this intensity and viscosity ratio and change this one to 1.5% and this 10 viscosity ratio, and I will keep the other values here. we'll press on apply and then close this window. So in the next step you will generate actually a steady state flow solution that will be used as an initial condition for the time dependent solution later on. So to do so, first I will go to the solution, and under the solution here I will select the method, click on this method here. I will keep this default value for this part, but I will go to modify the current number. To change the current number, you need again be under the solution here, then controls, and controls here, press here. So you have the current number here that you need to actually modify. Okay, so I will change this default value, this default current number from 5 to 25. Actually, this default value for density base is 5, but for relatively simple problem, setting the current number to 10, 20, or even 100 or even higher value, so it may be suitable and produce fast and stable convergence. However, if you encounter convergence difficulties at the start of the simulation of a properly set up problem, then you should consider setting the current number to its default value of 5. Then as the solution progresses, then you can start to gradually increase the current number until the final convergence reach. So this is important in the stability and run the solution. So I will retain the default values for the under relaxation factors here. Then to define the residual, you can find it under the solution, and under the reports you have access to this resolve. You have all of these options here in the outline view as well, like this monitor residual. In this case now I'm working here, so I can click on the residual here. So all of these values are 0.00. So I will keep this default value for now, just ensure that the plots is enabled in the options here on the group box, and also this print to console. So I will press on OK here, and now I'm going to create the surface report definition for mass flow rate at the flow exit here. So to do so, I need to go to the solution, and under the definition I will select the new, and under the new I will go to the surface report here, and then I will select the mass flow rate, this option, mass flow rate. So I will click on the mass flow rate to define this surface report definition. First of all, I will call this one as a outlet m dot, which is mass flow rate of the outlet. Then under the surface here you see it's a mass flow rate. So under the surface I will select the outlet here, and then just ensure about this report file, report plot, and also print to console. So I will click on this one and select it. So just as a note, when report file is enabled in the surface report definition dialog box, the mass flow rate history will be written to a file. If you don't enable this option, the history information will be lost when you exit ANSYS Fluent. So it is important, if you need this data, to keep this report file. So now I can click on the OK and close this window here. So if I go to the outline here, and under the report definition, so I have this actually outline m dot, and if I open this monitor report file and the reports plot, actually this outlet m dot plot and file are automatically generated by Fluent, and appeared in this tree here. As you can see, this is the file and this is the plot. Just I'm going to modify this output file name, so you should go here and then right click and edit this report file, and then I can change this. So for in this file name I will write it as stdm.r file out, because this is for the actually std state, and then I will press OK. So this file is the data for the std solution. We will press on OK. Then in this step I can go to the file, write the case. So I will call it as nozzle underline ss std state. This is case file, so I will write ss for the std state part. So I will press on the OK. Then I will go to the initialization, and for the method I will keep this hybrid initialization, and then click on the initialize. So hybrid initialization is done, as you can see here. So as we have a coarse mesh actually in this geometry, it is important to do some steps to refine our mesh here. So I will enable automatic adaption, so that the solver periodically refine the mesh in the vicinity of the shocks. As the iterations progress, the shocks are identified by their large pressure gradient in some area like here. So if you keep this meshes shape in your mind, then you can actually compare this mesh with the refined mesh. So for automatic mesh adaption, you need to go to the domain, and under this domain I will go to the adapt, and then I will select the automatic one. There are different options, manual or automatic. I will select this automatic mesh adaption here. So to do so, I will go to this predefined criteria. There are some predefined criteria. I will go to the aerodynamic here, and under the shock indicator I will select the density base. As you can see here, I will select this. Then I will keep this 20 as the frequency or iteration here for the mesh adaption, and then press and click on the OK to close this automatic mesh adaption dialog box. Now it is time to start the iteration and calculation. So I will go again to the solution, and under the run calculation here, I will enter number of iteration as 400 iterations. You can also go to the outline view and double click on the run calculation. So you will see it has been updated automatically when you enter here, but it's 400. We'll keep the other settings here, like this reporting intervals and the other option, and then simply click on the calculator to start the STD flow simulation. Okay, so we have our mesh here, and then scale the residual here, and also this outline m.plot that we created before. So you can go and check this mass flow rate at the outlet here. Okay, now the solution has been converged, as you can see, after 400 iterations. So we can check the scaled residual and also our mass flow rate at the outlet here. So now I can go to the file and write case and data file. Press on OK, and here you will ask to overwrite on the previous case data. Okay, so now we can go and check the mass flux balance. So although the mass flow rate history indicates that the solution is converged, you should also check the mass flux throughout the domain to ensure that the mass is being conserved. So we should go to the results. Under the results, I will go to the reports, and then under the fluxes, I will click on the fluxes, and then I will use this mass flow rate here. So retain the default selection of the mass flow rate, as you can see here. Then I will select inlet and outlet in the boundary selection list, and then click on the compute and examine the value displayed in the dialog box here. So the net result is 0.001. Actually, the net mass imbalance should be a small fraction, for example 0.1% of the total flux throughout the system. So the imbalance is displayed here in the lower right field under the net results, as you can see. So if a significant imbalance occurs, you should decrease your residual tolerance by at least an order of magnitude and continue iterating. So now I can close this window for the flux reports. And because of our automatic adaption, we can review a mesh that results from automatic adaption performed during a computation. So I can go to the results, and under the graphic mesh I will create a new one here. I will call the mesh name as the mesh adapted. Then ensure that the edges and faces here are enabled in the option dialog box. Then I will deselect all and then select the symmetry from this surface list, and then click this save and display. So as you can see, this is a mesh refine, actually mesh adoption here in the area that we have a high gradient. So the cells in the regions of high pressure gradients have been refined, and if I open the initial mesh actually to compare, you can see the difference between this refined mesh and also the initial actually mesh, as you can see here. So as you can see, for example, here in these cells, the mesh divided and refined into some smaller mesh because here we have high pressure gradients, as you can see here, based on this mesh. Now I'm going to display the steady flow contours of the static pressure. So I can close this window and then go to the results. Under the graphics, I will select the new contour. So I will open this one, select the new contour here, as you can see. And I will call this contour name as a contour of pressure. I will select the pressure, static pressure here, and then select the symmetry, and then press on the save and display button here. Then now we can see, I will close this dialog box here, and now as you can see, this is a static pressure in the symmetry plane of our geometry. So the steady flow prediction shows the expected pressure distribution with low pressure near the nozzle throat, as you can see here, this blue area. Then I can also display the steady flow contour of Mach number. So I will do the same process. I will go to the graphic. Under the contour, I will select the new contour, I will call this one as a contour Mac, and then in the contour of I will select first the velocity, and in the sub menu I will select the Mac number, as you can see here, then select the symmetry surface, and then save and display. And now I can close this contour here. If you go to the outline view, and so under the results and graphic, as you can see under the contour, you have two different contours that you have recently created. Okay, so that's it for this actually part, for the steady part. So in this step, I will define a transient flow by specifying a transient pressure condition for the nozzle. So let's see. Okay, so I need to enable a time dependent flow calculation. So I will go to the setup, and under the general I can double click this general item, and then change this time from steady to transient. So I will select the transient, so I will get this message here. So as we discussed, the pressure at the outlet is defined as a wave shape profile, and it is described by the following equation, as you can see here. So now I need to go again to the boundary condition and outlet, double click to open the outlet boundary condition, pressure outlet, to edit this part. So here I need to select the expression from this gauge pressure. So I will open this window and select the expressions here. Then I need to enter the expression. So I have entered this value here, 0.12 multiplied by sine of this value. And so in this case, omega is 2200 radian per second, and exit pressure is 0.7369 atmosphere. And this value is to convert to SI units, so multiply by this value, as you can see here. Now after entering this value, I can press on apply. So I change this gauge pressure from a constant value to this expression, and then I can close this. So now I need to update the gradient adaption parameter for transient case. So I need to go to the domain, and then under the adapt automatic I will go here. So again, under this predefined criteria, aerodynamics shock indicator, I will select the actually density base and enter 25 for the frequency, and so that's okay. I can press on OK to close this window. Now I will go to modify the mass flow rate output file, actually report file definition. I can open the previous one that we have created. It's a text file. So all the data for the steady mass flow rate has been saved here in this text file. As you can see here, all the data has been saved for 400 iteration. So I can close this notepad and then start to modify the mass flow rate report. I will go to the solution. So here under the solution, I will go to the monitor and then report files. I can edit this output file, and this time I will change this name from std to actually transient. So I will call it as transient m.out r file.out. And as this is a transient, so I will select the time step. For get data every one time step, you can change it to iteration or flow time if you want, but I will keep as time step, and then press OK. So the file name has been changed to the transient. Now I will go to modify the mass flow rate out plot, actually report plot definition, again to the solution, monitor, report to files, and I will open this outlet m.r plot and edit this one. Then here, as you can see, data will be get every one time step. Just for this x-axis label, I will change this flow time also to the time step here, and then again press OK to close this edit report file. Now I can go to the file and write the case data for this transient. So I will call this time this file name as a Nozzle unsteady case h file, and then press on OK. Okay, so for this transient, I need to define the time step parameters. The selection of the time step is critical for accurate time-dependent flow prediction. So using a time step of 2.85 596 e minus 5 seconds, 100 time steps are required for one pressure cycle. So the pressure cycle begins and ends within the initial pressure at the nozzle exit with this actually setting. So I will go to the solution, and then for the run calculation I will go here and then define this value. So number of iteration 100, time step size I will put it as 2.85596 e minus 5, and I can put this one as 10, maximum iteration per time step, and then I will click on the calculate to start the transient simulation actually here. So by requesting 100 time step, actually we are asking ANSYS Fluent to compute one pressure cycle actually. So we didn't do any initialization because we have the initial value from our steady solution as the initial value for this transient solution. Okay, so finally we reached to final iteration. So as we discussed, based on our time step and the number of time steps, so you will see, we can see first the mass flow rate, which is for one pressure cycle. As you can see here, this is the mass flow rate, and this is the residual, as you can see in the residual plot. And the first part, as you can see, is 400 iteration, which is for our initial actually steady solution. So after this one, we use this data for the initialization data of the unsteady flow, and from here we have the unsteady flow. So this value is for 1000 unsteady flow iteration. Now let's look at the mesh in different stages. This is our initial mesh. As you can see here, it's a coarse mesh actually, and this is the mesh after refinement during the steady state simulation. As you can see, most of this actually grids divided into some small grids, depends on the gradient that we had in the simulation. And after that, this is the final mesh adaption during the unsteady simulation. If you see here, also we have some mesh refinement, as you can see here, when you compare this shape with the top one, with the middle one here. So as you can see, this is the effects of the automatic mesh during our run, as you can see here in this picture. Now here we can go to the contour, for pressure contour again, and just display the pressure contour here, and also the Mach number contours. I can just right click and display again. You can see it here in this graphics. This is the results of Mach contour for the unsteady simulations. Okay, and at the end I'm just going to create a path line to see the velocity path line into this nozzle. So I'm just going here and double click on the path lines to create a new path line. You can create a name for this one. So for example, path line for velocity. I will go to color by and select the velocity here and the velocity magnitude. So for the creating a path line, you need one surface or more to actually ask Fluent to release the fluid from that surface. So in this case, I'm going to select the inlet, so the flow coming in from this surface will be shown during into the domain actually. So I will click here, and then I can also go to the color map options. You have different options you can change. For the color map, the type is fluid velocity. You have access to lots of different field velocity. Here I am just going to show the flow feature for bright peaks. So I will select this one. I will go to edit, because here the maximum value is blue, but I'm going to reverse this color map. So I can simply click on the reverse here and then apply and then close here. You can also change the font size, font type, and some other different options, but I'm just click on apply and close this window. So first of all, I will just press on the save and display. It is on the pulse mode is in the single. So now this is the path line here. I can also change the view of this nozzle, and also you have access to one option, pulse. If you click on the pulse, then you will see the fluid releasing from this surface and flows through the nozzle here. So you can create a path line like this. You can also save this pulse as the animation. This is the option. You can just simply select this one and then save as an animation if you want. So I will just stop this one and then save and display again. So you can see here this path line. You can select different options and then try by yourself. This is the continuous and the continuous path line. I will select this time this one, and then also you can modify this path line. For example, you can change the type with line or line arrows, or different options for skipping some of those. So I will just close this one and go to isometric view to have a view from the isometric view. And this is actually our path line velocity path line during our nozzle. So that's it all for this course. I hope you learned some new points in this course, and thanks for watching.